So we were looking at linear temporal logic in the last class. So like every logic, there is a syntax for linear temporal logic. So we have these view these true, false, and uh, we have set of atomic propositions. So P is an atomic proposition. And then we have the Boolean connectives like uh, negation and then conjunction, and then we had the next and the until operators, right? And we also discussed the semantics, uh, which are basically on these words, infinite words, and um, we also talked about discrete case structures, right? Where you have the words which are like states, and then the states are labeled by, or the words are labeled by these atomic propositions, right? And then a run of the Kripke structure, it essentially induces such a computation. And we also had the semantics for LTL with respect to these induced computations. So suppose there is such a computation pi, and then pi satisfies, it will always satisfy true, it will never satisfy false. And uh, it satisfies p if p belongs to that A0, the initial letter. So if you recall, the sigma is the it's the power set of the atomic set of atomic propositions, right? That's how it's defined. And then you have like negation of phi, phi and phi conjunction, and then the next of phi 1, it will satisfy if from the so if we talk about like that this computation starts from the 0th position, then from the first position, like if you consider the suffix, that will satisfy phi 1, and then similarly phi 1, it satisfies phi 1 until phi 2 if there exists such a k such that the suffix starting from k, it satisfies phi 2, and then at every position which is strictly before that k, for all j which is strictly less than k, you have that this the suffix starting from the j, it satisfies phi 1, right? And we also discussed some of the derived operators like eventuality, which is like true until phi, eventually some you want to see the phi. And then g of phi is like always phi. So it's always you'd like to, at every time point, you'd like to see this phi. So it's called a linear temporal logic because you see that there is a time like these are discrete times, and there is a single such a timeline in some sense, right? And at every that time point, you are saying that you would like to satisfy the formula. So that's the idea. And then we also looked at this expansion and distributive laws, which is like if you say phi 1 until phi 2, then it's, or say phi until psi, then either psi holds now or phi has to hold true, and in the next step, so psi has to hold true or phi holds, and in the next timestamp again the same formula, that is phi until psi has to hold true, right? So this is the thing. And similarly you can have for eventuality and always. So if it's eventually, then it's either phi has to hold now or in the next step, again, eventually phi has to hold true. And what is globally phi? Like phi has to hold true now, as well as from the next step also you have to see globally or always phi. And we also looked at all these distributive operators, right? Like how the until and the eventuality and the next operators, they distribute over uh, disjunctions and conjunctions in some of the cases. Right? We saw also there are cases where it doesn't distribute. right? So, for example, this thing phi1 until phi2 and phi3, it's not the same as phi1 until phi2 and uh, phi1 until phi3, right? We saw this. And similarly, again, phi1 or phi2 until phi3, it's not the same as phi1 until phi3 or phi2 until phi3, right? Okay. And we also saw that until is the least solution of this expansion law. Huh? So if you have LTL formulas phi and psi, then we have that this the set of words phi until psi, this is the least set P such that word psi union this set. What is this set? It's the set of words satisfying phi such that starting from the that such that the suffix starting from A1 that belongs to P, and so this set is a subset of P. And we also saw that sigma omega, that is the entire set of all infinite words that satisfies this property, which is not quite uh, interesting. So we are interested in the list set, which is in essentially this set, right? So this is what we saw. I mean, essentially, if you see that this particular set, it satisfies this constraint. Like if you replace P with this set, it satisfies, and uh, among every P which satisfies this constraint, this particular set is included in that set P. Okay. Good. And we also looked at certain examples like stable properties, like which is eventually global, which is like a Kobushi kind of a thing. Then you can also talk about infinitely often, right? Which is like a Bushi thing and so on. And we also saw uh, some, if there are k processes, then if there is a request, and then it will be granted eventually, and until it is granted, you'd like to stay in the request state and so on and so forth. Then you can also model, let's say, mutual exclusion properties with LTL. And suppose you want to say like um, uh, it's like one of the two processes enters the critical section infinitely often. So you can write such properties. Um, but we are not talking essentially always. I mean, we may not be able to. I mean, we may not talk about, for example, fairness assumptions, things like that. Okay, and then finally we were talking about this weak until property. So what is the difference with the weak until property? In strong until, you say if there is a phi until psi, then psi has to eventually happen. If you talk about weak until, that phi weak until psi, then it's like phi strong until psi, or it can also be the case that psi never really occurs, but then phi has to hold true always, right? Always phi. So, um, so this is the weak until property. Okay. So phi until psi or globally this globally phi. Okay. And so if you just want to look at let's say that until and weak until, I mean these are dual as we saw. So if I say it's negation of phi until psi, negation of phi strong until psi. So what are the, I mean, what can happen? Like, so essentially we are saying that phi starts to hold and psi is not holding. And this can continue forever. Or it can be the case that at some point of time, phi stops holding and then psi is uh, not occurring, right? So this is like phi and not psi, weak until not phi and not psi. So this can also continue forever, right? So in that case, it violates the phi until psi property. And similarly, if I say negation of phi weak until psi, so it's like I can say that so again we are saying that phi continues to hold and then there is no psi, and then there is a point where phi ceases to hold. Phi ceases to hold, right? And then psi is also not. Okay, is it clear? Right. And now you can also express this globally phi in with the help of such weak until formula, right? Phi weak until false. So so what is the weak until? Like this is going to hold, and this may hold or this may not even hold. So we know that false never holds, in which case phi has to continue to hold. So this is like the globally or always phi. And phi until psi also you can express using the weak until, like it's phi weak until psi and eventually psi. And eventually can be expressed as using globally, not of g, not of psi, and so you get something like this. And then the expansion law. So how will the expansion law for weak until look like? It's essentially the same as strong until. So we are saying that phi weak until psi. So psi should, I mean, psi can hold at this time point, or if that is not the case, then phi has to hold, and phi has to hold now, and then from the next time instance, uh, again that phi becomes psi has to hold, right? So that's and then we also say that okay, so this is something we were talking about at the very end, that weak until has the greatest solution uh, to the expansion law. So when we are talking about the expansion law with respect to the strong until expansion law, like so this property that we have now, it's exactly the same as what we saw for the case of strong until, with the difference that now we say that this is actually a superset of this. Okay, so uh, we say that words phi weak until size is the greatest subset P. Okay, so that means every P. So first of all, this satisfies this property, and every P which satisfies such a property, it should be a subset of uh, these words phi weak until psi. Okay, so first we show that this indeed satisfies this property, right? That phi weak until psi. And this is, I think, kind of not too difficult to see. It follows from the definition, right? Phi weak until psi. If you just put replace the p here with this um, the set of words satisfying phi weak until psi, we can see that this indeed satisfies this constraint. Clear, right? So why is it so? Because uh, if you have a word which is satisfying the formula psi, then of course, uh, uh, so this is already in that in the set of words which satisfies words like phi weak until psi. If it starts immediately satisfying psi, it already satisfies phi weak until psi. If that is not the case, then you have like the set of currently it is satisfying phi, and from the next step it's satisfying weak that phi until phi weak until psi, right? So this is exactly the set of words which corresponds to phi weak until psi. Okay, so yeah, essentially like so the set of so this set words phi weak until psi, this satisfies this constraint. And now this follows from this follows from the definition of phi we cantil psi. Okay. Now we show that for all p satisfying this property, we have that p is a subset of words phi we cantil psi. Okay, we would like to show this. So the way we would like to show is like, suppose there exists a w, okay, which is not in words phi we cantil psi. Okay, and then we prove that w does not belong to p. Okay, so suppose w does not belong to phi we cantil psi. So clearly, see, if this is the case, then this implies that w does not belong to words psi. Okay. Now, if it happens that now w now does not belong to words phi we cantil psi, then what else can we say about this word w? What else can we say about the word w?
Then why is this the case? W does not belong to words. Because word of phi is a subset of phi. The psi is subset of words of phi.
So if w does not belong to words phi we cantil psi, right? Then w cannot belong to words of psi.
Right.
Is that clear? Because if w belongs to words psi already, right? So starting from the beginning, like, so how does w look like? So w is of the form a0, a1, a2, etc. Right? So if w satisfies psi already, then it implies w also satisfies phi weak until psi. Correct? That is true.
Yeah.
So if w does not satisfy phi weak until psi, then of course w will not. It's just a
negation.
I mean contrapositive, right? So if so this you understand, w satisfies phi implies that this should hold true. So if w does not satisfy this, then w cannot satisfy phi. Okay?
Yeah.
So that's what we are saying. If w does not belong to this, then w cannot be in words of psi. Right? What else can we say? If w does not belong to words phi weak until psi, if that is the case, then what else can we say?
Then it's not in the second set. It replace p by words of phi until psi.
So then we can say that there exists some k, right? If w does not belong to this thing, first of all, we can say this thing, right? We can say something more. What else can we say? That there exists some k where, yeah, like phi ceases to hold and psi is also not true there, correct? Phi ceases to hold and psi is also. So then we can say that there exists some k such that suppose ak plus 1, ak plus 2, like this, it satisfies not phi and not psi. Okay, and for all j less than k until then, so there will exist such a k where phi ceases to hold and psi is also not holding, and for all the j before k, phi holds true. Okay, phi holds true, but psi is not holding. Okay, so aj plus 1, etc. Here you have phi and not of psi. Okay, now we see that if this is the case, right? AK plus 1 negation of phi. So what is happening, like here, this does not, so AK plus 1, so this thing, AK plus 1, AK plus 2, it does not belong to words of phi. Clear? And it also does not belong to words of psi, right? So, and it also does not belong to words of psi. So clearly, so then what we have is that AK plus 1, this does not belong to P. Is it okay? Is it okay? So what is this? So just let's look at the condition here. So we are saying such words, so the words, such words are in P such that, like, if such a word is in P, if this word has to belong to, this word has to satisfy phi, as well as the suffix should also belong to P. Okay, if this word belongs to P and its suffix, the immediate suffix, like starting from A1, it belongs to P, then this word will belong to P, A0, A1, etc. If this satisfies phi and its suffix A1 starting from A1 is in P, then this word A0 starting from A0, this will be in P. Clear? Now, if the thing is that if it doesn't satisfy already, like if this is not in words of phi, then it is not in P anyway, right? So you need both the conditions. So it has to be, it has to satisfy phi, as well as the suffix starting from A1 has to be in P. So if this one itself is not satisfying phi, so already one of the conditions is getting violated, then it cannot be in P, correct? So since this does not satisfy phi, right? And also it's not satisfying psi. So this is like, it's not anyway not there in psi also, right? So then it is not in P. Okay? We agree?
Yeah.
Okay, clear? Okay. So now what can we say about AK minus 1, AK, AK plus 1, etc. Right? So here we say that this satisfies, this word satisfies phi. This word satisfies phi. But we saw that the suffix starting from here is not in P. Hence, this cannot be in P. Clear? Right? So now we are using the fact that, okay, this satisfies phi, but the suffix is not satisfying that it has to be included in P. Right? So the suffix is not inside P. Hence, AK minus 1, AK plus, AK plus 1, etc. This also is not in P. It does not belong to P. Correct? So you can then apply this a few finite number of times, another some K minus 1 times or so, right? And you get, so if you just repeat this, you get A0, A1, this thing does not belong to. Clear? So what did we prove? So this is the word W. Hence, W does not belong to P. Right? If so, we started with the fact that W does not belong to words of phi, weak until psi. We showed that W also does not belong to P. Okay, right? So, which means that if you take again the contrapositive, if W belongs to P, then W belongs to words phi weak until psi. Okay, so hence for all such sets P which satisfy this property, this is a subset of this phi weak until psi, right? And it is the greatest subset. That's why the phi weak until psi, it's the greatest subset, right? The proof is very similar to what we saw earlier with the until, strong until. right? It's now just that instead of greatest, there we had a least set, right? And here, so earlier we saw that the sigma omega satisfied that constraint. Here you can see that the empty set, like if you say the empty set, right, it indeed satisfies this constraint, right? So which is not quite interesting, right? So the greatest set here is interesting. Okay. So the empty set, for example, like uh, uh, yeah. So if you consider any p, like so the empty set, let's say you have the no word is there in the empty set, right? And so if I put here, let's say instead of, so if I replace the p with the empty set essentially, so the empty set satisfies this property because uh, words psi union such a set such that a1, a2, etc. belongs to this empty set. So this condition will not hold true for any word. Hence, this set will become empty, right? So words psi, which can be a non-empty set, is a superset of the empty set, right? So the empty set indeed satisfies this property. But we are not, I mean, this is not an interesting set, right? The greatest set here is interesting. Okay, good. So we will now talk about the weak until positive normal form. Okay. So what is a positive normal form? Here, the negation is allowed only on the literals. Okay. The negation, you can push the negation inside. Okay. So that's why we are going to have both conjunction and disjunctions. Like earlier when we saw that LTL formula, we had the conjunction, like we had the negation and the conjunction, and the negation was allowed on any arbitrary formula. But now in the positive normal form, we are going to allow the negation only on the literals. So you have true, false, P, negation P. You see that we don't have a negation phi, right? So we have conjunction, disjunction. Then this next until, we are also introducing the weak until in order to take care of the negation. It will allow us to push the negation inside. Okay, so that's why we are adding the weak until. So, so here we will just see how the negation is pushed inside. So this is something we saw, like if you have globally phi, so it's like the negation of eventually not phi. You can also write it in this way, right? So phi we can do false. Negation of true is false. Negation of false is true. Negation of phi is phi. Now, if you have negation of phi and psi, then you use the disjunction, correct? So you can push the negation inside. Negation of next. So right. So I think we have been using the it's here. So negation of next of phi is next negation of phi. And this is also we saw negation of phi weak until psi, right? So we saw the dual formula that you have phi, if phi until psi doesn't hold, that means that you have phi and psi is not holding, and then at some point of time it may be possible that phi also stops to hold, or it can continue, like just that phi continues to hold, but then psi is never holding, right? So this is like weak until. So you can indeed negate this phi weak until psi and push the negations inside with the weak until, right? And similarly, if you have the negation of phi weak until psi, now you can push the negation inside and use the dual form of the until. Clear? Okay, good. So just to give you some more another example. So what can we do here? Can we can you tell me, for example, like if we want to put the negation inside, what we are going to get here? So negation of always A until B or eventually C. Sorry, or next C, right? So what can you do here? Negation of this G. It is not the case that always this holds. Okay, we can do step by step.
That's
So-
not pointed.
Huh.
So f of not.
F of not of A until B or X of C. Right? So first you can write. Then what do we write?
So f of
Huh.
not of A until B
Yeah.
and x not C.
F of so this is like, I think you were right. So mm, there is another bracket I should put here. Is it matching now?
Yeah.
Okay. Okay. So it is negation of A until B and X of negation of C. Right? And then this we can also write as in what way? Negation of A until B is
A until not B
A and
and
not B,
weak until
weak until not A
not A.
and not B. Okay?
Yeah.
So this is this and X of not C. Okay? So this is the thing. Yeah. Okay. So you can write it in this way. You can push the negations inside. So yeah, we are not going to formally prove it, but now I think it's clear to you. Like we can indeed formally prove. How shall we prove such a thing? So what we state is the following: that for each LTL formula, when I say for each LTL formula, the one that we started with, where we had just the until and we had negation over all phi's. Not only it's not in positive normal form, but you allow the negation everywhere, like on any arbitrary phi, you allow the negation. Now we are saying that for such an LTL formula, right, we had until we had the conjunction. We did not talk about the disjunction because you can put a negation in the conjunction directly. There exists an equivalent LTL formula in weak until positive normal form, right? So this is, I think we are convinced enough. Like you can see such a things, like we can always push the negation inside, use the until to a weak until whenever there is a negation and vice versa. But how do you prove in general such a thing? I mean, I'm just sort of like, what is the idea?
Something like induction.
Something like induction on the structure of the formula, right? You will have the tree, and then you can say that, oh, well, I can do things on the leaf, right? And then let's say you can do it by the hypothesis, induction hypothesis will say you can do it up to certain height, and then you can use all the different operators, and then you can prove it, right? So that's the idea. I mean, if you want, you can try to formally prove it yourself, but it's kind of standard. Okay. One thing to note here is that the length of the formula when we are applying all these things, right? So for example, like whenever there is this negation we are applying, right? So these things are getting repeated, like the phi and the psi, they are getting repeated, okay? So every such occurrence of the negation can increase the size by, I mean, it can make the formula, the size of the formula increase by 2 times. I mean, you get a formula which is twice as large. And if you apply this multiple times, like you can get an exponential blow up. Okay. So again, for example, here you have like just consider that there is a this itself okay, or maybe there is this negation of psi here, and that itself has again an until or a weak until, and then you need to again push it inside. Again, it will produce two different instances of the thing, and it can just continue. And you can have an exponential sized formula when you are translating an LTL formula into a weak until PMF. Now, one thing here, maybe we should just try to observe that when we are saying that phi and not psi weak until this not phi and not psi, this is equivalent to saying like not psi weak until not phi and not psi. Like what are we saying? So we are saying that it is not the case that phi until psi. It's not the case that phi until psi, right? So we are saying that psi should not hold, psi should not hold, right? And uh, at some point of time, phi should, phi can cease to hold, okay? And it at this part, I mean, it doesn't really quite matter whether phi is holding true or phi is not holding true. Okay, it doesn't quite. I mean, all we are saying is that the psi is not holding true, and then the phi can be there or the phi may not be there, right? And I'm saying that it's like a weak until with a negation phi. So it is still like a little bit of saving here that I am removing this occurrence of the phi, but it can still be exponential because I mean I still have, let's say, the psi, this is occurring twice, like, okay. So it's just a little bit of a saving. I mean, if you're implementing, for example, this kind of things, then the resulting formula, of course, will be smaller here than here, but it's still exponential. Now, uh, in order to sort of like in order to kind of cope with this exponential blow up when you're translating from an LTL formula to this positive normal form, uh, we can introduce another operator, okay, which kind of will not lead to this exponential blow up. So this is called a release operator. Okay, so this is called a release operator. So what is the idea of the release operator? That here it says that psi remains true. Psi remains true. So phi release psi. It essentially says that psi will continue to hold, and when phi appears, then at that time psi will hold, but psi doesn't need to hold any further. So psi will continue to hold. Phi release psi means psi is there. Psi is continuing to hold true, and then when phi holds, then phi should hold at a position k where psi is also holding, but then beyond that, it's not required for psi to hold anymore.
But phi should.
But phi has to hold. Phi has to hold it. So what it essentially means that suppose you have such a uh, computation where psi is holding, okay, and then at some point of time the phi also holds true, okay, but now given that phi holds true here, it releases the psi. So now it's no longer necessary that psi has to hold true, okay. That is the idea. But here, like phi remains true until and including once phi becomes true. Okay, including that position where phi becomes true, psi has to still even hold there. And also the thing is that if phi never becomes true, if it is the case that phi is never becoming true, then psi will have to continue to hold forever. Okay, if phi is never becoming true, then psi will have to continue to hold forever. So now, if I say, look at this thing, that false release phi, false release phi. So what does it say? That phi has to hold, okay? And then at some point of time, false has to hold. When you can get rid of phi, or if false doesn't hold, then anyway phi has to hold, continue to hold forever, right? Now false anyway never holds. False will never hold. So phi will always have to continue to hold. So it's globally phi. Correct? So globally phi is like false release sign. Now what about phi release psi? What is the expansion law for this now? right? So psi, it says that psi has to hold. And then at some point of time, when phi is holding true, there also it has to hold true, but then after that you don't
So
need.
phi and psi, or phi and next of, sorry, psi and next of phi are psi.
So what are you saying? Psi has to hold and
Next of phi are psi,
next of phi are psi
or phi,
or phi.
or phi.
Okay. Okay. So let's look at this.
Oh,
So
wait, but we want phi to continue.
what?
No, that's not me. Here, don't we require phi to continue holding after
No, no, no.
phi releases?
No, no, not no. That's not required. Even like in the until formula, right? So if you say phi one until phi two, okay. So phi one until phi two, what does it say? Phi one has to hold, and then at some point of time, phi two has to hold. But we don't say that phi two has to hold forever after that. It's just that there should exist some time instance where phi two has to be true, strong until. Okay. So here, uh, what we are saying is that okay, psi will have to be uh, true now, okay, and then phi can be true, but if phi is not true, then in the next you will continue to hold the phi release sign, right? So this is perfectly good. Okay, so is it clear? Like the expansion law for release. Okay, so now this is maybe a small exercise that let's try to do it ourselves. So um, Um, so this is what the definition of the release as we discussed, right? So psi remains true until and including one phi becomes true. And if phi never becomes true, then psi has to hold forever, right? If it never becomes true, then psi has to hold forever. Now I am claiming that this is indeed the same as this. So phi release psi is the same as like negation phi until negation psi. Okay, negation phi until negation psi. So can we try to prove that they are indeed equivalent?
Maybe it would be nice to like simplify the right hand side first. Like we did negation of A and then B.
Right.
So what will that do?
Negation of A until negation of B. Ah, okay.
No, like we did negation of A until B, we can expand it to weak until thing.
Negation of A until B, like this you were saying? Yeah. So what it is like? So you have, for example, negation of A until B, it's like you have at some position either um, the thing is that either A continues to hold forever or there exists some position where like all these are negation of B, right?
Yeah.
And either this continues forever or the other thing that can happen is like um, or the other thing that can happen is like this continues forever. Here I can say, okay, sorry, this continues forever, or at some point of time, you have negation of A and negation of B, and right? So this is the lot of this thing.
So this is like A and negation of B, weak until negation of A and negation of B. So in this case, it will be
Yeah. So this is the weak until expansion that we saw, right? So A and negation of B, weak until negation of A and negation of B.
so the right hand side will be like phi and sorry, negation of phi and psi, weak until phi and psi.
Yeah, sure. So you were saying that this is like so if you want to talk about it in the weak until form, then it's like so this, right? So negation of phi until negation of psi and negation of this. So if you want to talk about the weak until form, of course, you will get what do you get? Like here you will get phi and psi.
Then you get
And
negation of psi and psi.
negation of phi and psi, right?
Yeah.
Yeah.
And so the release operator is saying the exact same thing, that either phi will always hold and either psi will always hold and phi will never hold, or at some point phi and psi both will hold.
Yeah. So now you can say that indeed the release operator says that at some point of time, either this phi and psi both are going to be true, and until then, what is happening? Like
Psi
not phi. Uh, yeah. So until then, not phi, and then psi has to be true, and so this is, or it can be the case that psi just continues to hold if phi never occurs, right? So I think with the weak until this is we can use using this. Yeah, good. So yeah, uh, this is of course this is fine. I mean, you can also try to see in this way, like which I will maybe skip. That if you consider a word which is, let's say, it satisfies not phi until negation of not phi until not psi, then if you just look at the semantics of the until, what does it mean? It says that it is negation of this property, right? Not phi until not psi, right? What does it mean? That it is not the case that there exists a j such that starting from j, uj, it will satisfy not psi. It is not the case that there exists such a j, and so the negation is over this entire thing. And for all I less than j, this ui is going to satisfy the negation of phi, right? I'm just expanding this portion here. So I'm putting the negation and I'm just expanding this portion here, right? And now you can take the negation over the exist, so it will be like a for all, and you can push things inside, and then the final thing that you are going to get, you will see that this will correspond to this operation. So what I would suggest is that you can try to just do it yourself and also get another way of like looking at it and get convinced that this is indeed true. But yeah, this is also fine, right? Okay. So we understand, or I mean, now we understand that indeed the release is it can be derived from the until operator using these negations, right? So, but the thing is that if we are not having these releases, then we have to use the negation on some arbitrary formula. If we use the release, then we can again push the negations inside. So this is what we are going to call it a release PLF, release positive normal form. So earlier we saw the weak until positive normal form, but the downside of it was like when you are translating an LTL formula to a weak until positive normal form, you are getting an exponential blow up. When now if we are using the release until positive normal form, we are not going to use the weak until any longer. We will have the until and the release operator, and that allows us to kind of get rid of this exponential blow up. Okay, so how does the release positive normal form look like? So now we have phi 1 until phi 2 and phi 1 release phi 2. Okay, and we saw this expansion law, and we also saw that the release is like this negation phi r phi release psi is negation of negation phi until negation psi, And we can also say that similarly, if I have negation of phi until psi, it's the same as negation of phi will be negation of psi. Okay, good. So we can indeed like push the negations inside. And yeah, okay. And similarly, if you also see here, like given this, let's say, given that this holds true, so now if I have, let's say, a negation of phi release psi, then this is equivalent to negation of phi until negation of psi. So we can push the negations inside. And this does not blow up the form. It's not increasing the occurrences of the number of phi's and number of psi's. Okay. So far, so good. Now we will come to this LTL model checking. Okay, LTL model checking and satisfiability. So we have this formula. Let's say we have an LTL formula, and there are two kind of natural questions that we can ask, right? One is the satisfiability question. Like given such a formula, is it satisfiable? So what is the meaning of satisfiability? Does there exist any word model which can satisfy the formula, right? And we did this for that MSO, for example, right? MSO over word. So what was the, how did we do this? What was our algorithm to check the satisfiability of an MSO formula?
Converted it into an automata and check for non-emptiness.
Yeah, so we converted it into an automator and we checked for non-emptiness. So the idea here will also be similar. Okay, so we will be translating this into an automaton and check for non-emptiness. So if the automaton is non-empty, then the formula is satisfiable. Okay. Okay, so yeah, just let me ask the online participants any questions on the things that we discussed so far on this syntax and semantics and the positive normal form and different positive normal forms so far?
No, no questions.
No questions? Okay. So yeah, so we talked about the satisfiability problem. The other thing that one can talk about is the model checking problem. So what is the model checking problem? That you are given a model, right? And you want to essentially check the correctness of this model, correctness with respect to certain specific properties. And these properties are given in the form of an LTL formula here, right? In this context, the property is given in the form of an LTL formula. So what you'd like to say is that given this model, does every execution or every computation of the model, does it satisfy the given property? The property is the property of interest, or does it violate the property? Does there exist any execution which can violate the property? So this is something which is undesirable. There should not be, like if the model is correct, it should not have any execution which violates the property, right? So in the model checking problem, the model here is given in the form of a Kripke structure. Okay, so you have the Kripke structure, and let's say we call it this K, and we have the LTL formula. Do all computations of K. Do all computations of K satisfy phi. So what is the thing? Like all the computations of K, we call it, let's say, the traces of this model K, whether it's a subset of the set of words which satisfy phi, right? That is what it translates to. So this model satisfies phi if and only if all the computations, that means the traces of K, it's a subset of the words which satisfy phi. Then we are fine, right? So this is the case if and only if you see now the subset is like this intersection, the complement, sorry, this intersection, the complement language, complement of words of psi, this is empty. Okay. And the complement language, one can also see that as a complement, as a language corresponding to the complement formula, right? So it's a language corresponding to the complement formula, right? So that's what. the negation of the formula. So you have traces of k intersection words of negation of phi is empty, right? So now what we are saying is that if we can construct an automaton for this, sorry, if we can construct an automaton for which accepts exactly this set of, the language of that automaton is exactly the set of words which satisfies this formula negation of phi, then we are saying that suppose that automaton is A, right? So the language of A is the set of words which satisfies negation of phi. Then we are saying that K, the Kripke structure satisfies phi if and only if the traces of K. So Kripke structure is like a model. So you already have, this is like, you can almost think of this as an automaton model, but now you have, instead of the labels on the transitions, you have the labels on the states or on the words. And then, so the language of this, right, or the traces of the system, of the model, intersection, the language of this automaton. Which automaton? Corresponding to the complement formula, right? The negation of that form. The automaton corresponding to that, that should be in, right? So the negation formula is like it can have something bad, right? So what we want to say is that any execution of the system should not have an intersection with such a bad word, right? It should not have an intersection with such a bad word. So that should be empty. So this is the model checking problem, right? And what we'll see later that there have been tools which have been implemented, like which does such model checking, and they are also used widely in the industry as well. Like, so when you are doing, for example, like building, let's say there is a hardware that people, some industry is making, and then essentially to check the correctness of this hardware with respect to some property, let's say some floating point arithmetic and things like that, you actually do a model checking. And then there's like not only for hardware, even for example, drivers and all, like in the operating system, there are the software model checkers also, which actually checks whether the properties that they are supposed to satisfy whether they're validated or not, right? And if you can, if the model checking, for example, tool says that it indeed does not violate the property, then you have a formal proof of saying that your implementation is correct, right? Which is different from testing in the sense, like if you have a code and if you are trying to test, what do? You have a set of test cases. You run your code on the set of test cases, and it just says that there may be some presence of a bug, right? But it cannot certify the absence of a bug, right? Whereas when you are talking about this model checking, and the model checking software gives you this certificate that indeed this piece of code is correct. It tells you that there is no bug there. It talks about absence of bug, whereas testing tells you about the presence of a bug, right? So this is one fundamental difference. Okay, so now we will talk about, okay, so we still have half an hour. So now we are going to talk about how do we translate the LTL formula to Büchi Automata, right? So we saw that LTL formulas are closed under negation, right? You can either take your original LTL formula, or you can take the one of these positive normal forms, and the LTL formulas are closed under negation. So if you have a phi, you can consider the negation of phi, and then you can construct the Büchi automaton, or like some kind of an automaton corresponding to that, and check for the non-emptiness, the intersection of the Kripke structure and that, right? So there are the traditional way of translating this LTL to an automaton is like translating the LTL formula to a GNBW. What is GNBW? What was GNBW? The generalized non-deterministic Büchi neural automaton. Okay, so that is the traditional way, but before which we will study in depth and in detail. But before we get into that, we will first look at an easier construction using alternating Bushy word automaton. Given that we have now studied alternating automaton, so we'll look at an easier construction, which is the alternating automaton, and then we'll look at this construction which produces a generalized Bushy automaton, and we'll look at its correctness and all those things in detail. So by the way, this construction, which possibly we'll mention again, it's called a Vardy-Wolper construction. I think it's Vardy-Wolper construction to the GNBW. I think it was somewhere in the late 80s. And this construction from LTL to GNBW, this particular work, it received a Nobel Prize for this work because it made the entire process of model checking quite practical and useful for the industry, and I mean, apart from the algorithmic aspects of it. Okay, so that's one thing. So let's start with this translation from LTL to alternating Bushy word automaton. So one thing that we should note here is that when I'm saying that this is a positive normal form, I mean that release positive normal form. So if you are given an LTL formula, if you are translating it to a release positive normal form, it involves no blow up. Okay. So first we define, given a formula, we are defining the closure of a form. We are going to define the closure of a formula. So what is the use of the closure of a formula? We'll see that the closure of a formula is like a set of subsets of the given formula. Suppose you are given a formula phi, you consider the closure of this formula phi. So the closure of the formula phi will have some like, when I say subset, it's like some sub formula, actually, some sub formula, and they will be the states of your automaton, right? So the states themselves are these sub formulas in the automaton that we are going to construct. So let's look at what is meant by the closure. So if you are given such a formula, let's say psi, then the closure is denoted by CL, the closure of psi. It's a set of all its subformulas. And if you want to define, given the psi, how you'd like to define the closure of psi, it's the smallest set of all such formulas that satisfy the following. Like, so psi itself belongs to closure of psi. Okay. And then if psi1 and psi2, or psi1 or psi2, psi1 until psi2, or psi1 release psi2, if these are in the closure of psi, then both psi1 as well as psi2, they are also in the closure. Okay. They are also in the closure. And similarly, if you have the next of psi is in the closure of psi, then psi is also in the closure of, say, next of psi1 is in the closure of psi, then psi1 is also in the closure of psi. Okay, right? So all the components, all the subformulas, all the components, they are also in the closure. Clear? So so let's look at this particular formula, P and XP, next of P and next P until Q, right? So is it kind of like, if you look at this formula, P and next P and next P until Q, so how does it look like? So it says that you have that P continues to hold, and at every point you have next P until Q. Okay, so okay, so what is happening here? Like, P is holding true, and then every time there is a P, so at the next position there has to be a P, and at some point, like, you also want the Q to hold true. Okay, so this is not quite Q or Q release P. Is it Q release P?
Is it like Q should occur infinitely often and P should be true forever?
What?
Because
No. So what does it say?
okay.
P and next P until Q.
Okay.
P and next P until Q. Right? So what does it say? That it says that P has to hold true. Whenever there is a P, P is holding true. Then in the next position also P has to hold true, as well as I mean, and in the next position X. I mean, okay, if P holds true, as well as XP until Q holds true. So XP until Q holds true means, like, either you have Q here which is holding true. If that is not the case, then XP has to hold true, right? So XP means like P has to hold true, and in the next position again you have that XP until Q, right? So I'm saying that P is true here. Then in the next position I can have a P, but then also I need to see a Q at some position, right? Right. So
So this is like the weak release. Like Q should appear at some.
Q should appear at some point, right? So this is not quite release in this. That's what I'm saying. Because Q release P is like, it can always say that P continues to hold true forever. That satisfies Q release P. Correct? But if Q doesn't hold, globally P is like that, globally P, always P. That satisfies also this, like a word in which you have only P's forever. That satisfies Q release P, right? But will that satisfy this formula? P and next P until Q?
No, because Q should occur.
Q should occur, right? At some point of time, Q should occur. So this is, I mean, so it's not quite the same. I mean, what I wanted to say is not quite the same, but like, okay. I mean, okay. But anyway, so what we are trying to now say is that let's look at the closure of this. So essentially the closure will be like, you have the whole formula xp until q, right? So this is there in the closure. So psi belongs to the closure, as well as you have, if you have psi1 and psi2, both psi1 and psi2 should be there. You have p as well as you have xp until q. You have psi1 until psi2, so both psi1 and psi2 should be there. So you have xp, also you have q, and if you have xp, then p should also be there. But p is already there, we are saying, right? So this is our the closure set. So closure of this is the set of these formulas. Okay, so now what we say is that for every LTL formula psi, there is an alternating Bushy-Watt automaton, which is not too difficult to see. Alternating Bushy-Watt automaton with so many states. When we say order, like, it's the size of the formula itself. What is the size of the formula? It's like you can consider all the different propositions, and then you have the sub formulas and the conjunctions, and so it's like or the connectives. So it's like the size of the sub formulas, and you can add the size of the connectives and all. Like, so that gives you the size of the formula. Okay, so pretty much you can think of, like, if you express the formula in the form of a tree, then the number of nodes in that formula will be the size of the formula. Okay. So what it says is that given an LTL formula psi, you can construct an alternating Bushy-Watt automaton which accepts the same language as that of the formula. Okay, good. So right, so when I say L of psi, it's essentially the set of words which satisfy psi, right? Okay, so how does this alternating Bushy-Watt automaton look like? So as I said, the states of that automaton, those are the formulas which are there in the closure. Okay, and you have this is your alphabet. So the alphabet remains the same, which is like this power set of the set of atomic propositions. And then you have the initial state. So what is the initial state? The initial state is the original formula, the input formula psi itself. That is the initial state. And the and we are going to talk about the transition relation delta, and we also have the set of accept or the set of good states. Okay, so we will see that the set of good states are essentially like how should they look like? Any it's not very easy to see, but do you have any kind of like any sort of guess on how the good states should look like? So this will be the states which will have the release formula. Okay, so it's not possibly so easy to see now, but when we'll talk about that the other construction where you directly go from the LTL formula to that NBW, then I think we'll get the more intuition where we'll try to discuss this in more detail. Okay, so for now we'll see some examples. Okay, first let's go through the description of the automaton, how the transition function, how it looks like. So yeah, so let's start with suppose. So what is P? P is an atomic proposition. And what is A? What is the form of A? What is the form of A?
Some subset of.
Some subset of atomic propositions, right? Because we are talking about delta of P comma A. A is a letter, right? A is a letter. So A belongs to this set, belongs to this set. So A is a subset of the set of atomic propositions, right? So now P is some atomic propositions, A is a subset of atomic propositions. So what do you think it will be? Like delta of P comma A. So you have a state, you are in a particular state where the formula is P. It's just an atomic proposition P, right? You are in a state, okay? The formula is P there, okay? And now I'm saying that I'm seeing a set of a letter A, which is a set of atomic propositions. So what do you think my, how should I define the delta of P comma A?
P and A. I'm not sure.
So, okay, so let me try to maybe say this, that when I'm constructing the ABW, okay, when I'm constructing the ABW, what do I want? Like, so my initial state is, what is my initial state? What is my initial state?
Psi.
My initial state is phi itself, okay,
Psi.
or psi, yeah, my initial state is psi. And the set of states is that closure over all the psi. The set of states is the closure of all the psi. Correct? The set of states is a closure. Like I mean, the set, like every individual formula in the closure is a state of my automaton, right? And my initial state is psi itself, right? So I'm saying like, so the intuition is like, so if I'm at a particular state, let's say Q, okay, let's say Q, which actually corresponds to a formula, let's say phi, right? The language accepted from that state Q is what? The language accepted from the state Q of that automaton is what is intuitively is
L of phi.
L of phi. Okay, the language accepted is the set of words which satisfy the formula phi. That is the idea of the construction. That is the invariant that you will follow in the construction. So every state you go, like if you go from state phi 1 to some phi 2, or it's actually an ABW, so you will have a formula. But suppose you reach a particular state where the label is phi 1, that means that the language that I'm going to accept from this state will be the set of words which will satisfy phi 1. Okay, so this is the intuition. So with this intuition, now you tell me, if I have, like let's say I have the P. So what does it mean that from this state, which all words should I satisfy? P is an atomic proposition. Language of P. What does it mean?
All the
Mm.
words which satisfy the P, like the constraints in P.
Yeah, all the words which satisfy P is an atomic proposition. All the words which satisfy the proposition P. What does it mean? Like the words will start with some set of, like it's an A0, A1 like this, right? This is how the words are. A2 like this. But A0 itself is a bunch of propositions, right? Which is like P1, P2, etc. Right? So now I'm saying that this word will satisfy P. When will it satisfy P? Like if this word W is of the form like this,
P.
W satisfies P when
P is in A.
P is in a knot, right? This is by the semantics we saw, right? If P belongs to a knot, right? So now delta of PA equal to what should we say?
True if P in A.
Very good. If true, if P belongs to A, false if P does not belong to A, right? False if P does not belong to A. Here, right? Similarly, delta of negation of PA, true if
P is not in A.
P is not in A, false if P belongs to A. Clear?
Yeah.
Right? So the words which are not satisfying P, right? So that means that it starts with this A0, right? It's not satisfying P. That means A0 should not contain P, right? Okay. What about delta of P1 and P2A? What should this be?
P1, comma A and P2, comma A.
Yeah. This is standard this thing, right? Like we saw the way we saw it in ABW, and here delta of P1A or delta of P2A. Okay. It's like we are trying to define the transition function again by using structural induction on the formula. That's all. We are just defining the transition function. Given a formula, given a letter, we are defining defining the transition function, and we are using structural induction. So how should the function look like? That's all we are saying. Given such a formula, how should the function look like? So it's like a delta of P1 or P2 comma A is like delta of P1A or delta of P2A. Okay. What about delta of X psi comma A?
It is equal to sign.
Exactly. It's just psi. Delta of X psi comma A. Why is it so?
Because it now just wants to check if what comes after that satisfies sign.
Right? So you are in a state, let's say you are in a state which has X of psi. You read A, right? So in the next state, you go and you have to satisfy psi. So if you are satisfying X psi from here, you read any letter, doesn't matter. A, B, C, D, whatever you are reading. You go to the next state and you are satisfying psi. Okay. So delta of X psi comma A is psi. Okay. Now if you understand this, then what about delta of phi1 until phi2 comma A? When is phi1 until phi2 satisfied?
Or next one.
So
Delta of phi 2
delta of phi2 comma A
or delta of it will just go to phi 1 until phi 1 until phi 2.
Yeah. Because in the next, right?
Yeah.
So in the next you are satisfying that phi1
Yes.
until phi2. So it's like this. Or so you will say if this is not the case, then first I will have to satisfy that phi1, right? So delta of phi1 comma A. Okay. Right? So you can think of like I'm saying that I have to satisfy phi1 until phi2 from here. Okay. I need an A, where should I go? Right? So either I'm already satisfying phi 2 here. If I'm satisfying phi 2 here, then you can decompose the formula into thinking like, okay, I'll just focus on the phi 2 part. Then it's like delta of phi 2 comma A. If that is not the case, then I focus on the phi 1 part, delta of phi 1A. And in the next state, I have to satisfy again phi 1 until phi 2. Clear? Okay. What about phi 1 release phi 2 A?
Delta phi to A
A
and
and
delta phi 1.
so what is the release? Like, so you have the phi 1 releases phi 2. Okay. So phi 2 is holding, and if that phi 1 appears, then we are good. Right?
Yeah.
If phi 1 doesn't appear, so at this point of time, phi 1 release phi 2. So phi 2 anyway has to hold true. If phi 1 now also holds, then we are good enough. If that is not the case, then from the next state, again you have to
Do the same.
do the same thing. Phi 1 release phi 2.
So, and delta of phi 1 or comma A and delta of phi 2 comma A. Like both are sets. Okay, it's already there common. Or phi 1 and phi 2.
Okay, good. Okay, yeah. So this is the thing. And here I'll just mention, and then it will be clearer later, that it consists of all formulas of closure of psi of the form phi 1 release phi 2. Okay. What we'll see is that when you are having it of this form, phi 1 release phi 2, then essentially when you are looking at the until formulas, like suppose phi 1, suppose some phi until psi, or some phi 1 until phi 2. Okay. So it will require you to see the phi 2. You cannot say just in that phi 1 until phi 2 forever. It will require you to see the phi 2. Okay. And that is when you will say that, okay, I am going to accept. Okay. So let's see some couple of examples. So let's try to build the alternating Büchi automaton for this formula. Okay. GFP, which is like false. Globally phi, if you remember, globally phi is like false release phi. Globally phi like false release phi. Right? Because you cannot have false release, so always it will be that phi has to continue. So and eventually phi is like true until p. FP is like true until p, eventually p. Right? So now if we see this, then what are the formulas that are there in that the closure? You have the whole formula, the GFP. You also have like the false and true, which we are, I mean, yeah, which we don't really always explicitly add. And then you have the true until p. This is there, and you also have p. Right? So you have GFP, you have FP, and then you have P. Now, can you just tell me what is delta of true until P? So let's just, can you just tell me what is delta of true until P with a P?
True.
It's written here, of course, but how do you get it? Let's,
Because P is there, so it has now seen a P, so it's true until P is satisfied.
but true until P is satisfied. Okay, and there was a disjunction here, right? So if you have an until, then there was a disjunction here. So true or true is like, so it's, so the true comes, you were saying like, it's because of the, because of this part, like the phi 2 part,
Yeah.
that P comma P, right? And then there is a disjunction.
Yeah.
So of course it will true or something. Okay, good. What about true until P empty? So how, what is this?
First part is not true, so the second part will come.
Second part will be true, right? So the delta of P comma phi is false, and then the disjunction part. So what is the disjunction part? So delta of true,
True and next of. So just go to the page.
right? So true comma phi and uh,
P.
and no, true until P,
100.
right? It's this,
Wait, yes.
right? So this is true until P. Sorry, true until P, right? So true comma something is always true. So you have true until P. So this is true until P, right? Good. What about the whole thing? So we have, these are the states we are trying to find the transitions, right? So what are the, what is my set of atomic propositions here? My AP is just P, right? And the subsets of is like you have this thing and you have the empty set, right? So these are my letters. My letters are the P, the set P, or it is the empty set. So we are looking at all the transitions here. What about when you consider GFP and P? Release. So what do you get? So what is the release like? So you have delta of phi 2 comma A, right? So delta of true until P comma P, right? So delta of true until P comma P is true already, right? We have seen this, right? So phi 2 comma, so this is what? Phi 1 or phi 2 comma A is phi 2 comma A and this part. So this part,
Bye.
true until P comma P, delta of this is already true,
Yes.
right? So you get the true there. There's a conjunction, so we will have to look at this part now. So what is this? Delta of phi 1 comma A is delta of false comma P.
No. False.
False comma something is always false, right? And then or the entire formula. The entire formula is that true false are true until P, which is GF. Clear? Okay. So is it okay for the online participants? Is it okay for the online participants? Or
Hi.
uh,
Yeah. So wait, I didn't understand fully this thing. So can you go back to the? Acha, first thing. Uh, the states. Why are we not considering the states true and false also?
the states, the true and false are like formulas. So in the ABW, like I mean, usually the
Right.
way we consider is like true is some kind of a formula. When you reach there, we don't explicitly construct states for true and false.
Mhm.
Like well, I mean, you can think of true and false as like whatever transition you are having from true, it is always true. Like it's like something like a reachability kind of a thing. Like once you reach false, then nothing can be true from there. It's always false. When you reach true, then it's always true. Like that.
Mm. Yes. Right. And okay. So can you
So
go back to the?
consider them as like, so whenever you are in true, it's like a self loop for entire sigma, and false also it's like a self loop with the entire sigma. So we don't consider construct explicitly the states, but it's kind of implicitly it's there.
Right, right. Yeah. So, can you go back to the previous page once? Uh,
Yeah.
so, acha. So I was imagining it in terms of the Kripke structure, how it will look like.
Uh-huh.
So this delta of P1 and P2 comma A is equal to delta of P1A and delta of P2A.
P2A.
Uh, so is it something like so? Uh, there okay. So there is a state P1 and P2. There is a state P1 and there is a state P2. So is
Yeah.
it? Matlab, the diagram will be something like that, right? So
Yeah.
and
Yeah. So we'll see. I mean, what we'll do is like once we have these particular the transition functions, we'll try to draw the automata ones. So I think then it will become clearer also.
okay.
Okay. Okay. So now let's look at the last this transition, which is like if you have false are true. So this is the entire formula, the psi, and then if you are having the empty set as the later. So what do you get here? Like so, this is again uh, delta of true until p, right?
Phi, which is true.
Delta of true until p phi, which is true until p, right? So we have this true until p, and so we have true until p, and what about the first thing, like which is delta of false comma phi, which is false, or or we have uh, the whole thing, right? The whole formula. So it is that
G.
false are 2
Yeah.
2 Okay. So this is the thing, right? So this is you see FP and GF. Okay. So now we also similarly have we also have the state P, and we can try to get, of course, the transitions corresponding to these things P and phi. I mean P comma P, delta of P comma P is true and delta of P comma phi is false. But I did not write them. The reason being, you see here that for all the transitions that we have, like for this state, we are going to true. Here we are going to FP, which is the same state here. Like so, this is like a self loop. So FP on phi, it comes back to FP. Here the GFP on phi goes to FP and GFP, and GFP comma P is like GFP, right? So we are never reaching the state P. The state P is unreachable. So that's why I did not write the transitions from that anyway. The initial state is the given form, the GFP, right? And the state P is not. It's there in the closure of course, closure of the formula, but it's not reachable. So this is how then our this thing looks like, our automaton looks like. So you have GFP, and when you are taking P, then you right GFP, and then you are taking P, you are in the same step GFP. When you are in FP and you read P, you go to true. FP you P, you go to true. FP on empty set, you have a self loop. And then GFP on the empty set, you have FP and GFP, right? So there's a conjunction here. You have a self loop as well as you are going there, right? Now let's try to see this intuitively. What is GFP? Globally, eventually P. It's like the Büchi condition, right? Globally, eventually P, right? So suppose after a while, you see a finite number of P's, and after a while, you don't see a P anymore. Okay, this is my initial state. So will that word be accepted? Why? What's happening? Like so, you are seeing a P, some number of P's. You are here, right? and after a while you see the, like suppose it's like p, then you see, just continue to see the 5. Okay, then what is happening? This is not my, why is this an accept state and this is not an accept state? Why is it so? How did we define the alpha?
R.
The formulas which are of the form phi1 are phi2, right? So this is of the form phi1 or phi2. This is not of the form that phi1 or phi. Okay. Fp, yeah, here it's not of the form. So this is my accept state, right? So if I see this p, and then the empty set after a while. So for the first some p's, I'll see this. I'll be here, and then when I see the empty, then I'll be here as well as I'm here. This is a conjunction. Note that this is a conjunction. So I have to accept from here as well as I have to accept from here. But if I continue to see the phi's, I'm not going to accept because I'm here. I have to see a p from the fp. I have to actually see a p in order to accept. Right? So, but now again, after a while, like suppose you see a p, right? So what happens then? Like after you see the phi, you are here, and then like it's a tree that you are making, right? It's a tree that you are making, and then when you see the p, then again you will be going to this particular state, right? So you can try to yeah, I mean like draw the tree and see how the run tree for this alternating automaton looks like for different input words. And
So basically, each time it sees a 5 branches.
each time it sees a
So it
5.
will need to keep seeing P.
Yeah, right. You need to keep seeing the piece. So you can try to draw the like given a particular such word where you have like the piece occurring infinitely often, you can try to see like how the run tree looks like, right?
Like all the files between two P's, they will kind of go to true once you see the next.
Exactly, right? So all the all the branches that you will be having, they will be like, if you see the piece infinitely often, then you will see that all the branches will be going to the true. Okay. Yeah. And there is one more example here, which is of this form p and next p until q. Okay. Again, you can do the same thing, and this is how the automaton looks like: p and next p. So this is the formula we were seeing earlier: p and next p until q. So uh, if you see a p, you are just here, right? And then at some point of time, because of the um, um, because of the q here, right? So at some point of time, you'd like to, and because of the next p, right? Because of the next p, you at some point of time you'd like to see a p and a q occurring together. Okay, so the p, so this thing, so what does it say? Like p has to hold, and then also it is the case that from also this is the case like this until formula has to hold, right? So in the next state you have the p, and this will be the case, like the p's will be holding until there is a q, but because of the next, right, it's like phi1 until phi2. So phi1 has to continue to hold, and then at some point of time the phi2 has to hold, but then there the phi1 can cease to hold, but here the phi1 itself is the next of p, right, where the phi1 is ceasing to hold, and then the phi2 has to hold. I mean, the phi1 may also continue to hold, but it's not necessary. But suppose there is a k where that q is holding, and for all j that phi1 has to hold, and the j at position k minus 1 xp has to hold. So that means that at position k minus 1 xp has to hold, that at position k both p and q are holding together, right? So you need to see both p and q together, and then you will reach such a true, you will reach the true, right, satisfy. If you only see q, right, so when I write q here, it means that q and not p, I'm not writing the negation, then you will not, this will not be accepted, right? So that's the idea. So this is the thing, and here there is no state which is an accept state. Like the alpha is an empty set. You are just accepting the words by reaching the truths, right? By satisfying the true condition. Okay. So this is this, and just one small remark is that uh, that okay, so I did not talk much about the proof of correctness. Like, so if you have, for example, this was the idea that if you have the formula phi in the closure of psi, then uh, when Si is in a state phi, then it essentially means that we are going to that from state phi accept the words which are in L of phi, right? So the words that are being accepted is there, and you can prove this using like again by using induction on the structure of the formula. For the atomic propositions we already saw, like you have the p and then the letter a, so p has to be in the a or p is not in the a, that works. The other cases it follows from the semantics of LTL and by induction, so you can try. We'll discuss this more for the when we do the direct translation from LTL to GNBW. And also it will require you to argue about the alpha, which is like those the release operator, things like that. And one thing that we see here as a conclusion, that when we are going from LTL to Büchi automaton, like given an LTL, I can directly translate to an NBW, which is what should be the size of the NBW. So what is the size of the ABW that we constructed?
Or the size
Of the formula, right? It's linear in the size of the formula, right? So the size of the closure, it's essentially linear in the size of the formula phi. Is it clear? Maybe we'll discuss later. But like the size of the closure, the set closure is linear in the size of the formula psi. Closure of psi, the size of closure of psi, that set is linear in the size of psi. Okay. Now if you consider an NBW, it will be exponential, right? So it's like you get a 3 raised to n because of the Miyano-Hayashi construction. But if you look at all these automaton, just one thing to note here is that all these automata, the loops have a single, like the cycles have a single state. These are self loops, right? Here, when you have the loop here, there is a self loop here. Similarly here, all the loops, all the cycles, the SCCs, they only have like a self loop. Okay, so this kind of automata are called very weak alternating automata. So these alternating automata that we are generating, this is called a very weak alternating automata. Right? Why is it weak? Because one thing is that like in the weak we say it like you can partition the states, right? One is either it's subset of alpha or it's disjoint from alpha, right? So one state anyway it will be either in alpha or it's disjoint. So it's anyway weak. And when the SCC has a single state, it's called a very weak, right? Very weak alternating automata. Okay. And one thing that is known is that for very weak alternating automaton, when you translate that into an NBW, then the blow up can be reduced from 3 raised to n to n times 2 raised to n. Okay, okay, so let's end here. Yeah, so I took a bit more time today. And But so we'll just go over this a bit more slowly in the next class, and then we'll start with the LTL to LBW translation, which is the more, I would say, standard way of doing the translation to the generalized Büchi word automata, and do that in the next lecture. So, any question before we end? Okay. Any question from the online participants?
No. Yeah, you just have to look at it again.
Okay, so we'll, yeah. Okay, so if there are no other questions, let me stop the recording for now.